600 miles of locked fault, 326 years of silence, 19 full ruptures buried in the last 10,000 years. Millions of people asleep on top of it tonight. And the clock that governs it has already run past its own average. The fault has a name: Cascadia. Most people who live within reach of it have never heard of it. It is the largest subduction zone in the continental United States. It is the only fault on the continent that can make a magnitude 9. It runs offshore, unseen, from Cape Mendocino in Northern California to the middle of Vancouver Island. Two plates meet there. The smaller one, the Juan de Fuca plate, is diving under the edge of North America. It moves about 1.5 inches a year, roughly the speed a fingernail grows. That much is ordinary. Plates move everywhere. But where the two surfaces actually touch, nothing moves at all. The seam is jammed. It has been jammed since the winter of 1700. For 3 centuries, the plate has kept pushing. The seam has refused to slip. And all of that motion has gone into bending the edge of the continent like a wooden board pressed hard at both ends. The board has not broken yet. It will. You do not have to imagine what a locked subduction zone does when it finally lets go. You can look at the ones that already have. Sumatra, the day after Christmas, 2004. Magnitude 9.1. The seafloor lurches. The ocean rises. Within hours, a tsunami has crossed the Indian Ocean and killed more than 225,000 people across 12 countries. Japan, March 2011. Magnitude 9.1. A wall of water climbs over the seawalls built to stop it, drives miles inland, and pushes the Fukushima nuclear plant into meltdown. Around 18,000 people die, most of them from the wave, not the shaking. And this was in the country on Earth best prepared for it. Chile, 1960. Magnitude 9.5. The most powerful earthquake ever recorded by instruments anywhere on Earth. It broke roughly 800 miles of fault in a single event. Its tsunami reaches Hawaii in about 15 hours and Japan in roughly a day, still lethal after crossing the whole Pacific. Alaska, 1964. Magnitude 9.2. The second most powerful ever measured. In parts of the coast, the ground itself rose or dropped by tens of feet in minutes. Every one of those was a subduction zone earthquake. Every one was the same machine as Cascadia. The same geometry. The same physics of a locked plate snapping free. And in every case, the land had kept a record of its own violence for centuries. Nobody alive knew how to read it. Here is the strangest fact in the whole story. There is no American written record of the Cascadia earthquake of 1700. No newspaper account, because there were no newspapers on that coast. No mission diary. No settler's letter home. The event that ruptured hundreds of miles of the Pacific margin left nothing in the archive of the people who would later build cities on top of it. For most of the 20th century, the hazard maps reflected exactly that silence. They marked the Pacific Northwest as quiet. A place of small, survivable shakes. Not a place that makes the largest earthquakes on the planet. The maps were wrong. And the thing that proved them wrong was not a satellite or a new instrument. It was a dead forest, standing in a saltwater marsh, waiting to be believed. So the real question was never whether Cascadia will rupture again. The rock has answered that 19 times over. The real questions are harder. Why was a fault that breaks every few centuries treated as harmless across nearly 100 years of coastal planning? Who decided that the absence of a written record meant the absence of danger? Why have Seattle and Portland grown into a corridor of millions directly above a fault the United States Geological Survey now ranks among the most dangerous in the country? What happens to that coastline when hundreds of miles of it drop several feet in 90 seconds and the ocean comes in behind the fall? And can a society that forgot one of the largest earthquakes in its own past recognize the next one in time to matter? By the end of this, it will be clear how 3 separate fields of science arrived at the same year, the same winter night, and nearly the same hour. Japanese harbor records. North American tree rings. Cores drilled from the deep ocean floor. It will be clear why every ghost cedar on that coast died in the same season. And it will be clear why the federal official in charge of disaster response for the entire region summed up what is coming in a single flat sentence. That sentence is where this ends. It begins in a marsh. In the mid-1980s, a geologist named Brian Atwater walked out into the tidal wetlands behind Willapa Bay on the southern Washington coast. He worked for the United States Geological Survey. He was not chasing a legend. He was following a hunch that the coast had moved. He carried a shovel and a hand core, the simple tools of someone who reads the ground by opening it. The first thing that was wrong was the smell. Salt, rising from ground that should have been freshwater meadow, well above the tide. He worked the core down into the soft black peat and drew it back up. The column that came out was striped, as if layered on purpose. At the top, the dark living peat of a modern salt marsh. Beneath it, a clean sheet of gray sand, an inch thick, out of place. The kind of sand the sea leaves, not a river. And beneath the sand, an older soil entirely. Black, fibrous, full of the roots of upland grasses and trees. The soil of a freshwater meadow that had once sat safely above the tide. It lay buried several feet down, flattened and preserved. As if a living field had been pressed under wet cement in a single motion and left there. Atwater did not stop at one core. He worked the coast, north and south. Dozens of sites. Hundreds of cores. The same signature appeared everywhere. Living marsh on top. A sheet of sand in the middle. And underneath, a drowned meadow that had gone below sea level all at once. Not slowly. Not with the seasons. In one motion. And there was one more thing standing in those marshes that no core was needed to see. Trees. The bleached skeletons of western red cedar. Bone pale, bark and branches long gone, rooted in mud now soaked with salt. Red cedar is a rot-resistant wood, which is part of why it survived to be found. Beside it, in places, stood the buried stumps of Sitka spruce, a softer tree that had not lasted as well. Hundreds of them across miles of coast, big enough to have lived a century or more before they died. Their roots gripped ground that had once been dry meadow, high and safe. They had died on their feet and never fallen. The picture assembled slowly, and then all at once. At some point, recent by the standards of geology, this whole coast had dropped several feet in an instant. The sea had rushed into the new low ground. A wave had spread that gray sand across the buried meadow. And the cedars, roots suddenly full of salt water, had died where they stood. The land never rose back. The trees were not just evidence. They were a clock. The problem was that nobody yet knew how to read the time off them. For that, Atwater brought in a tree ring specialist named David Yamaguchi. A tree ring is 1 year of a tree's life, written in wood. A wide ring is a good, wet season. A narrow ring is a hard, dry one. Match the pattern of wide and narrow years in a dead tree against the same pattern in living trees nearby, and you can pin the dead tree to the calendar. To a single year, reaching back centuries. Yamaguchi cored the outermost wood of the ghost cedars at Willapa Bay, the last rings they ever grew. He compared them against living cedars from the same forests, then against trees at Copales, at Netarts Bay in Oregon, up the Columbia. The answer came back the same everywhere. The final complete ring on those trees was the ring for the year 1699. They had grown through the summer of 1699. They had not grown at all the next spring. They died sometime between the end of that last season and the start of the next. Between the autumn of 1699 and the spring of 1700, all of them, in the same narrow window, across hundreds of miles of coast. The catastrophe now had a year. What it did not have was a night. A tree ring can pin a death to a season. It cannot tell you the day or the hour. Beyond the year, the wood had nothing more to say. And a year was not enough. A year is not proof of an earthquake. A slow winter storm can drown a coastal forest in one bad season. A gradual creep of rising sea level can kill a marsh over a decade and leave a similar scar. To be sure the culprit was a great earthquake, the evidence needed a single moment. A night when the land moved so fast that the ocean flooded in and simply never left. Without that, the drowned forest was only a story about something that happened sometime. The marsh had given everything it could give. The trees had spoken to the limit of what trees can say. To find the hour, the scientists needed a witness on the far side of the planet. And there was one. It had been sitting in an archive for almost 300 years. Written in Old Japanese. In coastal towns that had felt the wave, but never the earthquake that made it. In the first weeks of 1700, a wave came ashore along the eastern coast of Japan. It arrived in the dark, without warning. The records of several villages describe the same night in nearly the same words. The sea rose on its own, with no storm behind it. It flooded the rice fields. It tore apart storehouses along the shore. It swamped boats sitting at anchor in the harbors. The water surged in over the course of a day in a series of pulses. Then it withdrew. There had been no earthquake felt on the coast. No storm out at sea. In Japan, a country that had catalogued its quakes and waves for 1,000 years, this made no sense. A wave that size always came after shaking you could feel. The word tsunami is bound to the ground shaking that comes first. A wave with no local earthquake to explain it was something else. An orphan wave. A tsunami with no visible parent. The village officials did what officials do. One headman wrote down the date, tallied the ruined rice, and filed for relief from his lord. And then the paper sat, unread by anyone who might connect it to a coast 4,800 miles away for nearly 3 centuries. In 1996, a Japanese seismologist named Kenji Satake, working with 3 colleagues, published the connection in the journal Nature. Satake had gone through the old coastal records. The height of the water at one harbor. The boats lost at another. The flooded paddies at a third. The records came from a string of villages up and down the Honshu coast, each one describing the same strange night from a slightly different angle. Then he did something only modern tools allow. He took a tsunami model, the same physics used today to forecast where a wave will go and how tall it will stand, and he ran it backward. He started from the wave heights measured on the Japanese shore, and he asked the ocean one question. For a wave to arrive here, at this size, at this time, where was it born, and how large was the earthquake? The model returned one answer. The source lay on the far side of the Pacific, along the coast of North America, and it had to have been a magnitude 9 or greater. Nothing smaller could shove enough water to cross an entire ocean and still lift fishing boats off their moorings in Japan. The wave reached the Japanese coast in late January of 1700. Working back through the roughly 10 hours it takes a wave to cross the Pacific, Satake could place the earthquake on the evening of the 26th of January, 1700. At around 9 o'clock at night, local time, on the coast of what is now Washington and Oregon. A winter night. Cold. Overcast. Almost certainly raining. Atwater's dead trees had given the year. Yamaguchi's rings narrowed it to the winter. Satake's harbor records supplied the hour. 3 independent lines of evidence. 2 countries. An ocean and 3 centuries apart. And they agreed. It helps to understand plainly what happened in the rock, because the mechanism is the whole story. In a subduction zone, a slab of dense ocean crust slides down beneath a slab of lighter continental crust. The 2 surfaces do not glide past each other. The friction is enormous. Along the shallow part of the boundary, they lock and stop moving entirely. But the deeper plate does not stop. It keeps pressing forward at its steady 1.5 inches a year. That motion cannot vanish. So it goes into deforming the plate above. The edge of the continent bulges up and squeezes in. It stores the strain, the way a wooden ruler stores it when you press both ends toward each other. The ruler bends. It holds. It bends a little more. For a few centuries, the bending just accumulates, invisibly out at sea. Then, the lock fails. All at once. Along hundreds of miles, at nearly the same instant, the bent edge of the continent springs back toward the shape it wants. The seafloor jumps forward and upward by tens of feet in under a minute, and the entire column of ocean sitting on top is thrown upward with it. That heave of water is the tsunami. The longer the fault stayed locked, the more strain it stored, and the harder the snap. Cascadia had been locked for centuries before it broke in 1700. The release was among the largest bursts of energy any fault on Earth can produce. The wave reached Japan before the earthquake ever reached the written memory of the country where it happened. There is one more thing the modern instruments have found. Every year or so, deep beneath the coast, the plates slip a little, quietly, in a slow-motion event that lasts days and shakes nothing at the surface. These silent slips relieve strain far down on the fault. But they do not touch the shallow, locked part near the coast. That part stays jammed. It is still loading. It is still waiting. But one rupture, however well dated, is a single data point. A year. An hour. One witness on each shore of the Pacific. It proved that Cascadia can make a great earthquake. It did not prove that Cascadia does it on a schedule, again and again, across the deep past. That answer would not come from a marsh or an archive. It would come from the floor of the ocean itself. The third witness came from the deep sea. Chris Goldfinger is a marine geologist at Oregon State University. For decades, he and his colleagues have pulled long cores of sediment out of the Pacific seafloor off Oregon and Washington. These are not the short cores of a coastal marsh. They come up the length of a bus. Columns of ocean bottom, striped layer on layer, like a cake sliced clean through. Most of the layers are pale. The slow, ordinary drizzle of sediment settling through quiet water, year after year. But between them run darker, coarser bands. Those bands are the record of violence. A dark band is a turbidite. When the seafloor is shaken hard enough, the loose sediment stacked along the walls of the submarine canyons breaks free all at once. It mixes into a dense slurry of sand and mud. It races down the canyon into the deep basin like an underwater avalanche. When it finally settles, the heaviest grains drop first and the finest silt last. It leaves a single, graded layer, coarse at the bottom, fading upward. Each dark band is the fingerprint of one such event. And a turbidite that large, appearing at the same moment in many separate canyons strung along hundreds of miles of coast, is very hard to explain with anything but one enormous earthquake shaking the whole margin at once. A local landslide can dirty one canyon. It cannot dirty every canyon along the coast in the same instant. Goldfinger's team cataloged these dark bands, canyon after canyon, down the Cascadia margin. From off Vancouver Island to Cape Mendocino. They counted them. They dated them with radiocarbon from the tiny marine organisms trapped in each layer. And they cross-matched the pattern from one canyon to the next. Exactly the way Yamaguchi had matched tree rings. They counted only the bands that showed up at the same time in widely separated cores. A single site could be fooled by a local slump. The whole margin firing at once could not. What they found was a history. Their record reaches back through the whole Holocene, roughly the last 10,000 years. Partway down the section sits a marker they could trust completely. A layer of volcanic ash from the eruption that formed Crater Lake about 7,700 years ago. It gives the core a fixed date to measure from. Roughly 19 full margin ruptures, earthquakes that broke the entire length of the fault across the last 10,000 years. Plus around 22 smaller ruptures, confined mostly to the southern segment. Something like 41 major earthquakes in all written in the mud. Something like 41 major earthquakes in all written in the mud. And the youngest dark band, the topmost layer of violence in every core, dated to 1700. The same year as Atwater's drowned trees. The same event as Satake's orphan wave. The intervals between those events were not random. Averaged across the whole fault, great margin-wide ruptures come roughly every 500 years. But the real spacing swings widely. from as little as 2 centuries to as much as 1,000 years. The southern segment, off Oregon and Northern California, breaks more often on its own, closer to every 200 to 300 years. The record shows the fault has not gone longer than several centuries without breaking somewhere, and it has now been 326 years since the last rupture of any kind. In that time, the Juan de Fuca plate has not paused. It has kept sliding east at its 1.5 inches a year, and along the locked seam, every one of those years has been quietly added to the account. 3 centuries of it works out to something like 20 feet or more of stored slip, waiting along the length of the fault. That is more strain energy than was released by any earthquake anywhere on Earth in the entire 20th century. When the lock finally fails, all of it comes out in a few minutes. If the deep history of the planet and the catastrophes hidden inside the rock pull you in, this is the channel for it. Consider subscribing and turning on notifications. There are many more of these stories ahead. Most of them are not in any textbook. Now, to the part that turns geology into consequence. The federal government has already modeled what happens when Cascadia lets go. And the man who led disaster planning for the region reduced the whole projection to one sentence. Kenneth Murphy directed Region 10 of the Federal Emergency Management Agency. That is the division responsible for Alaska, Idaho, Oregon, and Washington. Asked what a full rupture would do to the Pacific Northwest, Murphy answered in 8 words. Our operating assumption is that everything west of Interstate 5 will be toast. Interstate 5 is the freeway that runs north to south through the region, inland of the coast. It threads Seattle, Tacoma, Olympia, Portland, Salem, and Eugene. Everything to the west of that line is what he meant. Every coastal town, every port, every bridge, the whole Oregon coast, the whole Washington coast, the southern end of Vancouver Island. The projected magnitude is around 9. The shaking will last not the few seconds most people picture. It will last between 3 and 5 minutes. American building codes are generally designed around 30 seconds of strong motion. 5 minutes is an order of magnitude beyond that. Long enough to walk a fair distance while the floor keeps moving. Long enough to watch a brick wall come apart, one row at a time. Long enough to watch a coastline change shape while you look at it. Then the land itself drops. Subduction earthquakes pull the coast down over the rupture. By several feet. In some places, by as much as 6. The ground Atwater found drowned in Willapa Bay had fallen about 5 feet in 1700. The ghost cedar stood as its marker for 3 centuries. That same sudden drop will happen again. Along the whole length of the break. In the span of the shaking. And then the water comes. The tsunami from a full rupture is projected to reach the nearest coastal towns within 15 to 30 minutes. In some places, less. Modeled wave heights at the shore run from tens of feet up toward 100, depending on the shape of each bay. 30 feet is a 3-story building arriving as a wall. 100 feet is a 10-story tower. There is no version of that where an organized evacuation happens after the wave is moving. There is only the time it takes to get uphill on your own feet. In the dark. In winter. Assuming the road is still there. The bridge still standing. The route still passable after minutes of shaking have already torn at it. The federal casualty model puts numbers on what that magnitude means for people. On the order of 13,000 dead. Most of them from the wave, not the shaking. Picture a coastal town of a few thousand, sitting low on a sand spit between the open ocean and a bay, with no high ground inside the window. The model does not assume most of that town gets out. It assumes most of it does not. Another 27,000 injured, pinned under collapsed walls, walking out in the dark, cut off from hospitals that are themselves inside the disaster zone. Around 1 million people displaced. Their homes still standing, or half standing, but with no water, no power, no sewer, no road that reaches anywhere outside the ruin. For weeks. In places, for months. Roughly 3/4 of the buildings in the region predate modern earthquake codes. Oregon had no seismic code at all until the 1970s. Few places in the Northwest had one built for a magnitude 9 until the 1990s. The vast majority of the region went up before that, and a great many of those buildings are the ones a response depends on. Fire stations, police stations, hospitals, emergency operations centers. The structures built to run the rescue sit inside the zone that will need rescuing. Estimates suggest about half the region's highway bridges, most of its rail, and a large share of its hospitals will be knocked out or compromised in the shaking. The weakness runs deeper than any single building. The major ports of Seattle, Tacoma, and Portland are built partly on artificial fill. Loose engineered soil that acts like solid ground until it is shaken for minutes. Then it can liquefy and flow like a heavy liquid. The container terminals that move a huge share of American trade with Asia sit on that fill. The fuel depots that supply the region sit on that fill. The pipelines that feed the region's fuel run across it, with little redundancy behind them. State transportation officials in Oregon have estimated that well over 1,000 bridges could collapse or become impassable. And some of the roads carrying those bridges are the same coastal routes people would need to escape on. The federal estimates put full restoration of basic services, water, power, fuel, at somewhere between 1 and 3 years after the event. And they admit that some coastal communities may never be rebuilt at all. This is not a worst-case fantasy built to frighten. It is the central estimate of federal planning, resting on the same evidence the geologists gathered. Atwater's Marsh, Satake's Harbor Records, Goldfinger's Cores, a modeled rupture releasing centuries of stored slip along the length of the fault. It is not a prediction of when. It is a description of what. And there was a fourth witness. One the science was slow to let into the room. Ruth Ludwin, a seismologist at the University of Washington, spent the late 1990s gathering the oral traditions of the coastal indigenous nations. The Coast Salish peoples, the Quileute, the Maka, the Ho, the Hu-ai-at on Vancouver Island, and others down the coast. These were accounts carried in spoken language for 10 generations or more. Earlier scholars had too often filed them under folklore, under myth. Rather than treating them as testimony, they describe the same night, a winter darkness, ground that shook so long and so hard that people could not stay on their feet. The sea drawing back from the shore, far out, bearing seabed no living person had seen. And then a wave returning behind it, taller than the standing trees. It swallowed villages. It tore away canoes. It drowned whole communities of people sleeping in their winter houses on the beach. Some traditions carried an explanation for the cause in the language of story. Along parts of the coast, the shaking and the wave were told as a struggle between the thunderbird of the sky and the whale of the sea. A sky creature seizing a sea creature. The earth convulsing and the ocean answering. Other nations remembered specific losses. The canoes that came back from the water to find their village simply gone. The night the sea came up over the spit and carried sleeping people away, leaving only those who had been on high ground. These were not decorations on a legend. They were reports. Ludwin compared the genealogies attached to several traditions, counting generations of named ancestors back from the present, against the time markers inside the stories themselves. The counts landed, again and again, on the same narrow window. The turn of the 18th century. The winter of 1700. The same winter as the dead cedars. The same winter as the orphan wave in Japan. So now there were 4 witnesses, entirely independent, none of them in contact across the centuries. A Japanese official in 1700 who wrote down the height of a strange wave and the date it came. A forest of American cedar trees that died in a single season and kept the year in their rings. A library of cores from the deep Pacific floor that recorded the dark band of one enormous underwater avalanche. And an unbroken chain of spoken memory along the whole coast, told in dozens of distinct languages, describing the night the sea came in. 4 sources, 4 formats, 4 cultures, 1 conclusion. The earthquake struck around 9 in the evening on the 26th of January, 1700. Its magnitude was near 9. The rupture ran the length of the margin, from northern California to Vancouver Island. The coast dropped several feet along the entire break. A tsunami crossed the Pacific in under half a day. The whole event was finished inside a single winter night. The forgetting then was never a failure of evidence. The evidence had been preserved, carefully, by 4 different cultures, across 2 continents, in 4 different media: wood and paper and mud and human memory. The failure was in who was permitted to count as a witness. For most of the 20th century, American seismologists looked for the kind of record they were trained to trust: written records in English. They found none, and they concluded the coast was calm. They did not go looking in Japanese harbor archives. They did not read the tree rings until Atwater pulled the first core. They did not sample the deep-sea sediment until Goldfinger's teams went out and drilled it. And for a long time, they did not sit down with the people whose ancestors had stood on that shore the night the wave came and ask them what they remembered. The Cascadia earthquake of 1700 is now the most thoroughly documented prehistoric earthquake on Earth. The point is that it was documented the entire time. It simply was not heard. The cedar trees are still there. 326 years after the night that killed them, their bleached trunks still stand rooted in the salt marshes of Willapa Bay and Netharts Bay, weathering down slowly, falling one at a time, but still there. They are the longest-lived witnesses to a catastrophe that the country built on top of them never wrote down. Some things have changed since they were the only ones speaking. The West Coast states have funded a system called Shake Alert, a network of well over 1,000 seismic sensors strung down the coast. It is built to catch the first faint motion of a rupture and push out a warning before the slow, destructive shaking reaches distant cities. In the best case, that warning buys a few seconds, maybe up to a minute. A few seconds is enough to slow a train before the track moves, enough to close a gas valve, enough to get under a desk before the ceiling comes down. It is not, and cannot be, enough to evacuate a coastline. Schools and hospitals in the danger zone are being reinforced, one building at a time, on whatever budget the legislatures can find. Some bridges have been rebuilt. Hazard maps of liquefaction, of tsunami inundation, of expected shaking have been published by the Geological Survey. Coastal towns have posted evacuation routes on their street signs. A handful have built vertical evacuation towers, concrete pillars tall enough to lift a few hundred people above the water. There is one more turn to the story. It is the story of how the story finally got told. In July of 2015, the writer Catherine Schultz published a piece in The New Yorker. It was titled "The Really Big One." It laid out, in plain and unflinching prose, what a full Cascadia rupture would do to the Pacific Northwest. It carried Kenneth Murphy's sentence about Interstate 5 to a national audience. The following year, it won a Pulitzer Prize. For a huge number of Americans, that article in 2015 was the first they had ever heard of the fault. More than 3 centuries after the earthquake had already happened. Generations after the first settlers built the first cabins on top of it. For 30 years before that piece ran, almost no one outside a small circle of scientists knew the fault had ever produced a great earthquake at all. The odds are not abstract. Scientists now put the chance of a large Cascadia earthquake in the next 50 years at roughly 1 in 3. The chance of a full margin 9 at roughly 1 in 10? Those are the real measures of progress. The sensors and the towers and the reinforced schools and the national attention. They are also nowhere near enough. And everyone working on it knows it. The deeper question Cascadia leaves behind is not really about earthquakes at all. It is about how many other catastrophes are already written into the world, in formats the people at risk have not learned to read. How many ghost forests are standing right now in other marshes dated by no one? How many ledgers sit in foreign archives describing a wave whose parent has never been found? How many oral histories are still being told in languages that no institution is recording? How many dark bands of sediment wait in cores that have not been pulled from the sea? How many coastlines, on how many continents, are running the same silent clock toward the same moment, with no one keeping the time? The Cascadia earthquake of 1700 was never truly unknown. It was unaddressed.